Hello, for data communications and network 1 class today, I will talk about the topic digital modulation. And this is the topic that continues from the last clip, okay, which is digital data to analog signal. So this one is digital data and we send, okay, with analog signal. Now, why do we have to do that? Okay, because in order to transmit a signal through a transmission medium, okay, or a transmission medium, okay, the signal needs to be not modulated to the appropriate frequency range, okay, as you know from the clip on the transmission medium, okay, we have learned that different frequency range has different characteristics, okay, some is a ground wave, some is a sky wave, some is a wireless transmission with line of sight communications like microwave, okay. So if you want to transmit your data, okay, with an analog signal, it has to be in the correct or appropriate range of frequency, okay. Now, for example, for wireless communications, okay, we will use the antenna, right, to send and to receive the data. If you look at the formula, C equal to F lambda, where C is the speed of light, okay, so 3 times 10 to the 8 meters per second, right? And your frequency, right? And then lambda. So if you look at voice frequency, you may have maybe you have wondered why voice frequency we never use an antenna to transmit voice frequency for telecommunications, okay? Let's say voice frequency is around 3 times 10 cube, okay, or 3K hertz, okay? So what is lambda? Lambda will be equal to 10 to the 5th meters. So we say that the antenna size has to be at least 1/10 of the wavelength, okay? So 1/10 of the wavelength would be 10 to the 4th meter, okay? This is too large to use in practice, okay? So we never use antenna to transmit voice, people voice, okay, or human voice directly, okay? But if we modulate it, okay, suppose we modulate it to 100 megahertz, which is a radio signal frequency range, okay? So C equal to F lambda. C is 3 times 10 to the 8. F is 10 to the 8, right? 10 megahertz is 10 to the 8. Then lambda. Lambda will equal to 3 meters. And then 1/10 of lambda is just 30 centimeters. This is much nicer. Okay, we can have antenna with the size of 30 centimeters, right? Okay, so this is why we have to send in the, in the frequency range that is suitable. And we can see that higher frequency will lead to smaller antennas. Okay, if you use even higher frequency than this, like satellite communications, okay, we will need even smaller antenna. Okay, now let's look at the encoding techniques for the digital modulation. There are basically 4 techniques. Okay, the first one is called ASK or amplitude-shift keying. This one will change the amplitude of the carrier, okay, of the carrier signal. Okay, so we will put digital data into the amplitude of the carrier signal. For the FSK or frequency shift keying, we put the data into the frequency of the carrier. Okay, phase shift keying, we put the data into the phase of the carrier, and the QAM, we put the data into the digital data into the amplitude and the phase, okay, of the carrier. Now let's look at examples, okay, for the ASK. So the first one is like line coding that we have seen before. So you have constant amplitude, right? One is like maybe 5 volts, 0 is like 0 volt, okay? But in the ASK that we want to transmit, we modulate it, okay, to the appropriate frequency. So one we send with some frequency like this, some waveform, okay. One we have the same waveform, but 0 we send nothing, okay. By sending nothing in 0, for 0 bit, and then send the waveform for bit 1, okay, we call this on-off keying. This is a special case of the amplitude-shift keying. Okay, on-off keying means send and not send. Okay, this will save the energy, right? Because if it's 0, we don't have to send anything. Now let's look at the frequency shift keying. In this case, we use two different frequencies, okay? So we have F1 and maybe F0. So for bit 1, we send waveform with one frequency. For bit 0, we send waveform with a lower frequency, something like that. Okay, so you can see that by looking at the frequency of the FSK signal, we know that this is 1 or 0. Okay. For all cases, okay, the resulting signal, it will be in the bandwidth that's centered around the carrier frequency. So if the carrier frequency is in the range that is suitable for your antenna size, you can send that signal. Now let's look at the ASK in more detail. Okay, suppose for an example, I use bit 1, okay, as a cosine 2 pi FCT. So this is my waveform. It can be a cosine or a sine. Okay, usually we use sinusoid signal. Okay, and bit 0 we send nothing. Okay, this can be actually B cosine 2 pi FCT. Okay, so like different amplitude, right? But I set B to 0 here, so it's become on-off keying. Okay. This one, since the information is in the amplitude, okay, it's highly susceptible to noise because noise adds to the amplitude. So if you send something like this, and you add noise, okay, this is noise, then you receive something like this, okay. Sometimes you are like not sure, okay, how many bit one is this, okay. So it's, and if you have impulse noise, okay, that is very high amplitude, then it will ruin everything. Okay, we have talked about this before also. So it will make everything look like a high voltage, something like that. Okay, in that range. Okay, for application of the ASK, even though it's not very good, I mean highly susceptible to noise like this, but we can use it in the application of optical fiber, and we call this intensity modulation. We send by light and dark. Okay, so it's on-off keying. Light and dark, okay. And in the optical fiber, we don't have much noise, okay. It's usually isolated from the noise, so we don't have much noise, and that's why it's work in fiber optics, okay, for ASK. Now let's look at the next one, frequency shift keying or FSK. This is less susceptible to noise, okay, than the ASK, so you can use it in like wireless communication, okay. So we use it in radio transmission. We use this in LAN. Okay, we have the binary and non-binary case. For the binary case, it means that you use one bit, okay, to represent one symbol, right? So you have bit 1 and bit 0. You use two frequency, F1 and F0, okay, to represent two pulses or two pulse shape, okay, of S1T and S2T. Usually, the frequency F1, F0 and F1, okay, this is FC, this is the carrier frequency. Usually it's offset, okay, by the same frequency delta. Okay, so this one is the frequency domain. Okay, and this is the carrier, cosine carrier. Okay, it can be sine also. Now for the FSK, which is the non-binary case, which means that M is more than 2. Okay. For example, if M equal to 4, then you have 4 cases. Okay, 0, 1, 2, 3. You represent 0, 0, 0, 1, 1, 0, 1, 1. So you represent 2 bits per symbols. Okay. The number of bits per symbols that you can represent equal to log base 2 of M. So log base 2 of 4 equal to 2 bits per symbols. Okay, so this one I use 4 different frequency, F1, F0, F1, F2, F3, okay, and the same amplitude, okay, and the same shape of cosine, okay, it can be sine or cosine also with different frequency. So this is for the binary case, I have FC and this is delta, right? For the binary case, I have F0, F1, F2 until Fm minus 1. And this is different by delta. Okay. For this, okay, for this, we have minimum, okay, value of delta here. This one can be delta over 2. Okay, we have the minimum value of delta, okay, to make it orthogonal. But I don't want to talk about this here because in principle of communication class, there will be, detailed talk on this. So this one is only overview, okay, because it's very like small topic in our class, okay. So just know that there is a minimum delta, okay, that is preferred, okay. So if you use 4 FSK, so you have 4 frequency, right? If you use 8 FSK, the frequency, the bandwidth here will be bigger. If you use 16 FSK, bandwidth that you need will be even bigger, okay, because you have minimum of delta and then you have to increase, increase the frequency, number of frequency. This one you use 4 frequency, and then this one use 8 frequency, this one use 16 frequency, okay, so please just know that. But when you increase the number here, M here, then you can represent more bit per symbol, like 16 FSK you can represent like 4 bit per symbols, and then 8 FSK you represent 3 bit per symbol, something like that, okay. Now let's look at the PSK, or the phase shift keying. The phase shift keying, okay, we change the phase, so we have 2 phase, pi and 0 here, nothing here, so it means 0. This is for the binary case of bit 1 and bit 0, okay. This is not susceptible to noise because, again, noise attack the amplitude, okay, of the signal, okay, noise add to the amplitude of the signal. So if the information is in the phase, okay, it will not get much effect by noise. For the FSKs also, the information of FSK is in the frequency, so again, it's not susceptible to noise, okay. So both are good, FSK and PSK in this case. But PSK is better, okay, in terms of the bandwidth limitation. I just tell you that if you use like 16 FSK, you have to increase the bandwidth, right? Okay, but for the PSK, we do not need to increase the bandwidth, okay? We can use the same bandwidth. So this is good, okay? We can send more data if you use non-binary PSK, okay? Like MPSK, we can send more data over, okay, by using the same data rate. The data rate is the symbol per second, okay? The number of symbol per second that you are sending, okay. So this is the baud rate. Okay, now we will talk about the differential PSK, okay. Differential PSK is a form of differential encoding that we have seen in the NRCI, okay. You can see that the inversion, okay, at the beginning of the bit, okay, will tell you whether it's 1 or 0, right? So if it has inversion, it means bit 1, okay. So this one has inversion of the phase, bit 1, inversion of the phase, bit 1, no inversion, bit 0, has inversion, bit 1, no inversion, bit 0, something like this, okay. So this is this picture is a kind of a differential encoding example, okay. Now we will look at the non-binary PSK. Q is the quadrature, okay, which means 4, okay. So quadrature phase shift keying of 4 PSK. This one we use 4 phase, right? So 4 phase, so you can represent, so M equal to 4, so you can represent 2 bit per symbols, okay. And so you can double the data rate, okay, using the same symbols per second, number of symbols per second that you are sending. For QPSK, as an examples, okay, I have 0, 0, 0, 1, 1, 1, 1, 0. So we have 4 different values. So I have 4 phases: pi over 4, 3 pi over 4, 5 pi over 4, and then 7 pi over 4. Okay, and then this represent 4 signal. Okay. Now you may notice that this one look a little bit strange. Okay. Usually for binary code is 0, 0, 0, 1, 1, 0, 1, 1, right? But this one is 1, 0, and then 1, 1, 1. 0, 1, and then 1, 1, okay? So this is called gray code, okay? This is an example of how you represent a bit in the PSK, okay? Now, why do we do that? Because you can see that for the gray code, adjacent symbols, okay, has only one bit different, okay? So 0, 0 to 0, 1, one bit different. 0, 1 to 1, 1, okay, only one bit different. 1, 1 to 1, 0, okay, only one bit different. And then this one, only one bit different. Why do we do that, okay? Actually, in the next clip, I plan to talk to you about the constellation diagram, okay? This will help you understand more on the digital modulation, okay? But right now, because of the adjacent symbol have only one bit different, let me draw the constellation, simple constellation for you, okay? And we'll talk about this again in the next clip, okay? I have 4 signals here. This is S00, okay? And then this is S01, S11, and S10. When something is wrong, okay, usually it will be wrong for the adjacent symbols, okay? So by making adjacent symbol has only one bit different, mean that one symbol error equal to one bit error, okay? But if I don't do this, if I have 0001, 1011 in the binary case, this is 2-bit difference, okay? So if there are something wrong, okay, this one symbol error will cause 2-bit difference, okay? And this one is also causing 2-bit difference, okay? That's why sometimes we will use the gray code. We can also assign it differently, okay, not using the gray code, okay? This is an example. Anyway, since I talk about gray code, let me give you an example or tell you how to construct the gray code, okay? When I construct the gray code, I have to do it like n equal to 1, n equal to 2, I mean increasing bit by bit, okay? So let's say this, n equal to 1, I have 0 and 1, this is my gray code, right? Now n equal to 2, what do? I have 0, 1, and then I have a mirror here, and then I have 1, 0. As you see, I put the mirror here, and I reflect it back, so it becomes 0, 1, 1, 0, and then I add 0 in front in the first half, and then 1 in the second half, okay? So I have 0, 0, 0, 1, 1, 1, 1, 0, okay? The same as what I show you here, okay? And then I put, again, so I have the 2-bit, right? I want to make the 3-bit. What do? I put the mirror here, okay? So I have 0, 0, 0, 1, 1, 1, 1, 0, and I have the mirror here. I reflect back to 1, 0, 1, 1, 0, 1, 0, 0 like this. And then I put 0 for the first half and then 1 for the second half. So this is my gray code for the n equal to 3, or if I want to use 8 PSK, I can use gray code for my 8 PSK here, okay? If I want to use 4, okay, what do? So you use the n equal to 3, okay, 8 code here, 8 code right here, and you put the mirror, okay, here, and then reflect back, okay, reflect back here, and then put 0 for the first half, okay, and 1 for the second half, like this, and then you have n equal to 4 case, okay? As I say, it can be assigned differently, okay? And the phase can also be any other phase, okay? That are equally apart. So I can use the phase 0, pi over 2, pi, 3 pi over 2, something like this, okay, instead of the pi over 4 case. But they have to be equally apart to be a good encoding, okay? Example of MPSK, as I say, 8 PSK or 16 PSK. If you want to use 8 PSK, it means that you need to add 4 more phases in between here. So let's say I have this, okay, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, 7 pi over 4. So I have 8 phases, okay? Now you can see that the noise immunity, okay, how you can be correct, okay? Even though there is a noise, this ability will decrease, okay, with higher M, okay? Because you have to distinguish the values of the phase, okay, that are closer together. If the phase is 0 and pi, for binary case, okay, it's 0 and pi, right? So it's easy to distinguish whether this symbol is pi or 0 phase. But if you have 0 and 4 over, pi over 4, this is more difficult, okay, to distinguish. And if you have 16 PSK, you have to divide this into pi over 8. So it will be even more difficult to distinguish, okay? And we'll see how you solve this problem with the QAM in the next clip. Okay, thank you very much.